Hello, good evening. All right, this is going to be part 2 of lecture 4 of CENG 4412. And this is going to be continuing up from our lecture but last Thursday, which covered some of the beginning theory of tension element design. Now, for part 2, all I'm going to do is work through the remainder of the theory, covering the equations and theory for connecting element design. Then I plan to pause the recording and work through a example problem for the third part of the lesson. Now, I know this is definitely a record for the for a delay in terms of the part 1 versus part 2 recording. Got a bit delayed, but I do want to record this and then continue with lecture 5 for our actual class period tomorrow. Okay, so let's continue on here. Continuing right where we left off on Thursday, September 14th. Okay, so let's look at the last bit of theory here, and that's connecting elements in tension. So as a review, we had, in terms of general structural design, members or anything, at least in a frame structure, members are your long longitudinal elements, beams, columns, etc., while connecting elements are those things that connect them together. So, connecting elements in tension. Connecting elements in tension. First of all, let's review our general equation for loading, or for LRFD load design, for LRFD design. So, if you remember in general LRFD, load resistance factor design, our overarching equation, this will be our main overarching equation for the entire semester, goes something like this. And this is gamma sub I, Q nominal I, maybe a summation here if you wish, perhaps a sigma, must be less than or equal to phi r sub n. Phi r sub n. So again, what are these things? Let's annotate a bit. This is going to be our ultimate factored loading. Ultimate factored load. And this is going to be our factored resistance. This is produced through various load combinations, 1.2 dead plus 1.6 live, that kind of thing, or 1.4 dead, etc. And factored resistance will be, you'll have your resistance factor. And as we saw previously, or in the first part of the lesson, this resistance factor will vary based on what type of loading, well, actually not type of loading, what type of member and also what type of failure mode you're investigating. For example, yielding will have a higher resistance factor than fracture because that tends to be fracture tends to be a more dangerous form of failure than yielding. Okay, next, let's consider the two things that we want to look at today. I want to lay out the equations for both fracture and yielding for connecting elements. Now, thankfully, they're not actually really any different for connecting elements versus tension versus members. Although we do add one extra check. Okay, sorry if my voice is a bit hoarse. It's been a long evening. Okay, but I did want to get this out there before our lecture tomorrow. Not that I expect y'all to review it before 8 a.m. tomorrow. Okay, so let's look at yielding here. So again, this is our general equation, but then we will have some subforms of this, or more specialized forms of this, more specific forms of this, depending on what type of member we have and what type of failure mode we're looking at. So let's look at fracture. Let's look at yielding first. Yielding, well, let's see. So I don't feel I need to include this part of the equation because this is the same load combinations that we've seen many times before. And then, so what I really want to focus on is this VRN portion. And in the case of yielding for connecting members, or sorry, for connecting elements, need to be more specific with my language. VRN is going to be equal to phi times Fy area gross, FyAg, where phi again is phi is our phi is going to be our resistance factor, Fy is our yield strength, and Ag is our gross area. The gross cross-sectional area of our connecting element. And in terms of where this is, let me provide you a citation here. This here is equation J 4-1 in the connecting element section. And this is page 16.1-137 in the 15th edition of the AISC Steel Manual. Okay. And again, this phi here is going to be 0.9 for yielding. Next, we have fracture. Don't need that. Next, we must consider fracture. And in the first portion of the lecture, we did thoroughly discuss the difference between yielding and fracture. And here, phi, Fu, well, actually, let me start with the same phi Rn. Phi Rn is going to be equal to phi, Fu, F ultimate, times Ae, where Ae is the effective net area, as we discussed previously. And, again, this here, I want to provide the equation number and page for y'all. This is going to be equation, just right after this one, J 4-2 on page, again, 16.1, dash 137 of the 15th edition of the AISC Steel Manual. Okay, here, but we do have one other special check that we have to do specifically for connecting elements in tension. And this comes out of field observations and laboratory studies. So one final special check for connecting elements, one final special check, and this is more of a geometric check than a purely strength check. For connecting elements, this is sort of a good design check. A good design check that comes from that comes out of field explorations, field surveys, and laboratory experiments. So this is sort of a general rule that has developed out of either formal studies or also say forensic investigations of failed structures, that kind of thing, and lab experiments. As a general rule, we have found that, well, again, connection, the reason we have this kind of geometric rule is that most of the things that we're going to do, again, most of the things that we're going to do are strength dependent. We actually calculate okay, this connection can withstand this many kips of tension in this direction, or this column can withstand this many kips of compression, etc. But sometimes there are things we learn just sort of as rules of thumb, or rules of thumb was maybe a bit too rough. More empirical relationships would probably be a better way of stating this. And so we have a rule from the code that says that we want to, it's sort of a geometric rule on connecting element design. So connecting element geometric rule. And this is something we do want to design for. So here's the thing. For connecting elements, we don't really have anywhere in the code or as we discussed the shear lag factor previously, the U, the capital U. So That applies for long longitudinal members. You do get that kind of stress concentration, that tensile stress concentration in a long longitudinal member. But in connecting elements, we don't have that. So for connecting elements, U is essentially always 0, unless your connecting element is unusually long or something. U is essentially always 1.0. So area net is basically area effective. Again, previously in the first portion of the lecture, or in the previous video, we discussed the difference between net area and effective area. But in connecting elements, area net is effectively the same thing as area effective. So because of this, again, from experimental case studies, from experiments, from field work, from case studies, from failure studies, etc. Structural engineers have kind of developed a good rule of thumb, and this, you may find this embedded within the code somewhere as well. And this is just something I want you to consider and keep in mind in all of your design problems and calculations that we go through. And what we want to do is, we want to limit, at least for connecting elements, this doesn't apply to tension members or any other elements, but if we have a connecting element in tension, for all connecting elements in tension, we want to have a geometric check of area nominal is less than or equal to 0.85 area gross. Your gross area. So again, this is not based on raw strength. We're not actually going to be calculating the strength of these. This is not something based on strength. This is not a kind of case where we're calculating, okay, well, this section has this kind of capacity in kips. Here's our load. This is more of a geometric check where we say, okay, we've seen that if we let this thing go, if we let the net area go over 85% of the gross area, we tend to run into problems with connecting elements. So instead, we just say, okay, this is, we don't, to actually, yes, we could use something like a very elaborate finite element model or a finite element computer analysis or something. But if we're doing this by hand, if we're just doing simple hand calculations, let's instead just use a simple rule of thumb that says for connecting elements in tension, we are going to purposely limit ourselves to never have a net area less than 85% of the gross area. Okay, that'll conclude it for part 2, and part 3 will consist of a example problem, a numerical example problem, covering some of these topics. All right, thank you, and we'll be back.